Hello and welcome to all judges. My name is Halil Anwar Abdul Halim. On behalf of our research team, we would like to welcome to all of you. And for today's presentation, I will be presenting on our latest innovation on hybrid copper graphite field linear low density polyethylene flexible conductive polymer composite for electronic interconnect application. And this presentation is for Ereka 2026. So basically, a conductive polymer composites are created by combining between conductive material, such as metal and semi-metal, with polymeric material. This combination allows polymer material become conductive material due to the presence of conductive field flow from a path and to form a pathways that allow the electrical to flow in the polymer region. One of the advantages is that the CPC itself will have flexibility, lightweight nature, and ease of processability. And also, these material are likely to be widely used in application requiring flexibility and conductivity, including flexible printed circuit boards, wearable sensors, energy storage devices, and automotive electronics. The ability to replace traditional metal-based interconnects makes them a promising alternative for next-generation electronic and sustainable technologies. So why does the needs for flexible conductive polymer composite? Okay, so the question can be answered by several factors, which is that for CPCs, it possesses the flexibility and it when it are subject to mechanical deformation, they still can electrically conductive. Okay, and it also has high sensitivity and high electrical conductivity, which is the potential to be used as stretchable sensor with cyclic stability. And another point is that the simple fabrication process can be cost effective. Problem statement, okay. In general, the use of single filler will promote agglomeration, leading to poor dispersion and poor adhesion. Okay, so in this case, we're introducing hybrid filler to be combined with LLDP polymer matrix, and it can promote better filler dispersion that can form a good conductive network and improve mechanical properties. And in terms of cost effectiveness, processable and high performance LDP composite can be produced using this hybrid filler LLDPA conductive composites. So basically, there are three aims and goals, which is our research group has been targeted. Firstly, to investigate the effect of hybrid copper graphite filler loadings on the mechanical properties, and would like also to evaluate the electrical conductivity of the polymer composites, conductive polymer composites, and also to analyze the morphological physical structure of the polymer composites by the means of optical microscope and scanning electron microscopy SEM. So novelties of our innovation is that ability for our material to conductive electric and is the main novelties for this particular project. Okay, why? Because these fillers establish a network structure that meets the percolation threshold, enabling electrical conductivity. Therefore, this project highlights the potential of flexible conductive polymer composites for electronic interconnect applications. So basically, the concept or the idea of conductivity inside a polymer composite is where that we need to achieve the percolation threshold and also the ability of the filler itself to conduct electric by forming a network structure that can permit the conductivity pathways within the polymer composite. In terms of materials processing, okay, we use linear low density polyethylene as the main metric, polymer matrix, combined with copper and graphite, and using matte blending to process the material, which is processed at 160 degrees Celsius for 20 minutes at 15 revolution per minute using Z blade mixer to produce the LLDPE copper graphite conductive polymer composite. So these are several testing and characterization technique that was employed to investigate the to characterize and investigate the behavior or the performance of our conductive polymer composite, okay, such as tensile, hardness, 4-point probe, and optical microscopy, and also SEM for morphology analysis. In terms of tensile strength, as we can see that the addition of the hybrid copper and graphite at from 2 to 10% resulted in increase in the tensile strength. So this means that the mechanical properties of the main matrix at LDPE is improved. However, when we look at the elongation at break, we can see that although we seen there is improvement in terms of tensile strength, oppositely, the elongation at break was decreased, okay, with the increasing of the filler content, as we can see in the graph above. In terms of modulus, we can see that there's slightly differences whereby we can see at the 2 and 4% the modulus decreases. However, for 6 and 8% the modulus of velocity will increase, and for 10% we can see that the modulus also decrease if we compare back to pure LLDPE. So the decrease in the modulus is might be due to some outbreak of the sample might be have agglomeration of particles or the hybrid fillers within the composite material. In terms of hardness, you can see that with the increase of hybrid filler content, we can see that the shore hardness was also increased. In terms of electrical conductivity, we can see how does the influence of various hybrid copper loading had increased the electrical conductivity of the polymer composite due to incorporation of conductive filler, as in this case the copper and graphite. So it can be seen that in this case the increase in the electrical conductivity is due to the our material have reached the percolation threshold, which was the critical concentration contact filler that can transform from insulating to a conductive state. So if we compare between the result for tensile strength and electrical conductivity, we can find that both with the addition of hybrid fillers, conductive fillers, we can see that there were increase in tensile strength and electrical conductivity with the increase of the hybrid filler content. In terms of the morphology, so these are the particles for the filler that we are used in the compound, the hybrid filler that is used within the LLDPE conductive polymer composite, whereby the spherical consists of a copper particle, and at the bottom the flaky and agglomeration is for the graphite morphology. So if we look at the morphology, okay, we can see that obviously we can see the copper particle exists and the graphite particle were dispersed within the LLDPE matrix, and this is for 2 weight percent, and this is for 6 weight percent, where we can see that the numbers of dispersed copper and graphite will increase, and also for 10%, there are numbers of copper particles and graphite particle present within the matrix of LLDPE. So in this case, the potential application of this conductive polymer composite is wide, and it can be used in flexible smart devices, either in communication, healthcare, transportation, or even for robotics. So benefits of flexible surfaces can be, but not limited to, the flexibility and lightweight, and is lead-free and eco-friendly, and it can be customized and tunability with the cost-effective processing, and also it contains durability, and the material itself is durable and also had a mechanical resilience. So these are some latest publication that have been produced throughout for this research work, and also IP copyright that's been granted for this particular project, and also industry collaboration from Polytech and Nihon Superior. So these are references. These are references. So in summary, addition of hybrid filler composite graphite and copper improve the performance of composite. Increasing the hybrid filler content in composite leads to increased tensile strength, hardening elongation, and electrical conductivity. Then it can be identified that around 4 to 6% of hybrid filler content show a good formulation for this composite, where the composite achieves highest electrical efficiency while giving good mechanical performance. And also this project supports the SDG 9, which is industry, innovation, and infrastructure. Thank you.